Hello everyone, I welcome you to the Bloomberry Educare. This section is chemistry and today's topic is entropy and its characteristics. Entropy is a measure of degree of randomness or disorder in a thermodynamic system, and hence the entropy increases when matter is scattered. It's a thermodynamic state quantity represented by S. Like other extensive properties, enthalpy or the internal energy, entropy is also a state function. That means the entropy is a function of temperature, pressure, volume, or the number of moles. Hence entropy, in other words, depends on temperature, or we can write the entropy S is proportional to the temperature. And as the temperature increases, the entropy increases. As the temperature decreases, the entropy decreases. This is because with increase in temperature, the degree of randomness also increases because the molecules gain more kinetic energy. Change in entropy, that is delta S, can be calculated from the differences in the change in entropy from final to initial. At constant temperature, change in entropy is also given by another mathematical expression, that is delta S is equal to Q reversible system divided by T. This happens at constant temperature, or we can say in an isothermal condition. This equation can also be written in other form, wherein the entropy S is given by K log W. Let's represent this equation as equation A. In this equation, this K represents the Boltzmann's constant and W represents the thermodynamic probability. This equation A, is also known as the Boltzmann-Planck equation. This equation A clarifies that the entropy is also related to the thermodynamic probability of the system, that is W. The change in the entropy can be either positive or it can be negative. And the entropy is positive when the Q is absorbed, and it's negative when the Q is released. That also means that when the Q is absorbed or the heat is absorbed, in that case the entropy S increases. Whereas when the heat is released, the entropy S decreases. As the entropy increases, that also means the kinetic energy of the molecules also increases. Suppose you have a system and that is at low temperature, and you have another system that is at high temperature. Let's consider this as case 1 and this as case 2. In case 1, wherein the system is at low temperature, if we increase the temperature by X degrees Celsius, the entropy is going to be high and there is going to be more disorder. If you increase the temperature of a system that's already at a high temperature by the same amount of temperature as in case of the case 1, that is by X degrees Celsius, then in that case the entropy is going to be high, but it's not going to be as high as in case 1. That indirectly means that in a low temperature system, if you increase the temperature by X degrees Celsius, suddenly the entropy is going to be very high. Whereas in case of the system that's already at high temperature, if you increase the temperature by X degrees Celsius, the entropy is not going to change much because it's already at a higher value. In case of a cyclic process, the entropy change is always equal to 0. Also, in case of an equilibrium state, the entropy is also equal to 0. Now let's see about the entropy in case of different states of matter. Here we will consider 3 different states of matter, that is solid state or crystalline state, the liquid state, and the gaseous state, or what we also call as the vapor state. In case of solid state, let's represent the entropy by delta S solid. For liquid, let's represent it with delta S liquid, and for gaseous state we represent it as delta S vapor. Now in case of the solid state or the crystalline state, the entropy is highly ordered because the structure is compact, whereas in case of the liquid state, the entropy is of an intermediate order and it's of least order, or we can say it's highly random in case of a vapor or gaseous state. So if we have to rearrange these terms, we can say that delta S solid is always highly ordered as compared to the liquid, and which is always highly ordered as compared to the vapor state. The units of entropy are always joule per Kelvin. We can also measure it in terms of calorie per Kelvin in CGS system. Now we know that we can convert a solid state into a liquid state or liquid state into a gaseous state. That process is referred to as the phase transformation. For phase transformation, we can say that a solid can be converted into a liquid and a liquid can be converted into a vapor. Also, a solid can be directly converted into a vapor state. So these different types of phase transformations, if I represent them as 1, 2 and 3. So the phase transformation 1, that is when we convert any solid state to a liquid state, that is called as the entropy of fusion. So 1 will be called as the entropy of fusion, and the entropy of fusion is always given by this equation, that is delta S is equal to delta H by T, and this delta H is the delta H of fusion, and this equation is always at constant temperature, pressure, and here delta H is of fusion, that's the change in enthalpy is for the fusion only. Similarly, if we take the change in or the entropy of vaporization, that is when you convert anything from liquid to a vapor state. In that case, the delta S is given by delta H by T. This is again at constant temperature, pressure, and here delta H is of the vaporization. And now if we convert directly a solid into a vapor, that is phase transformation 3, in that case the entropy of sublimation, we call it as a sublimation. So sublimation is when a solid is directly converted into a vapor state. For example, in case of a dry ice, it's directly converted from solid to a vapor state. That in that case, the delta S is equal to delta H by T, where the temperature is constant and pressure is also constant, and this delta H is of sublimation. So as an example for the phase transformations, I am giving an example wherein we can convert ice to water, and then water can be converted into a vapor state. So when ice is converted to water, that is the entropy of fusion is required. In this case, we require around 220 joule per Kelvin. Then the ice will be converted into water, and similarly when water is converted into a vapor state, that is the entropy of vaporization. The entropy of vaporization is around 109 joule per Kelvin. So this concludes our lecture for the entropy and its characteristics. I hope that you guys liked this lecture. If you did like this lecture, please hit the subscribe button and hit the bell icon also, so that you can get notifications for the recently uploaded videos. Until next lecture, take care of yourself.